Data does not always survive the journey. Interference on a cable, a weak wireless signal, a fault in the hardware, any of these can flip a bit from a 0 to a 1 or a 1 to a 0. And here is the difficulty. The receiving device cannot tell. A corrupted byte is still a perfectly valid byte. It just means something different from what was sent. So every method in this lesson works the same way in outline. The sender calculates something extra from the data and sends it alongside. The receiver performs the identical calculation on what arrived and compares. If the two values disagree, the data changed on the way. There are 5 methods on the syllabus, and the examiner expects you to be able to describe the process for each one. The simplest is the parity bit. 1 bit of each byte is set aside. It carries no data of its own. Before sending, the sender counts the ones in the data bits and sets that spare bit so the total follows an agreed rule. Even parity means the total number of ones in the byte must come out even. Odd parity means it must come out odd. Both devices must agree which rule they are using before any data moves, because the same byte gets a different parity bit under each. Look at the example on the page. The data bits are 1, 0, 1, 1, 0, 1, 0. That is 4 ones. Under even parity, 4 is already even, so the parity bit is 0 and the byte is sent unchanged. Under odd parity, the same data would need a parity bit of 1, making 5 ones altogether. The receiver then counts the ones in the byte it received, and if the count breaks the agreed rule, something was corrupted. But a single parity bit is weak in 2 specific ways worth knowing. First, it only catches an odd number of flipped bits. If 2 bits in the same byte are corrupted, the count of ones changes by 2, the parity is unchanged, and the error sails through undetected. Second, even when it does catch an error, it tells you only that the byte is wrong. It cannot tell you which bit. So you know the data is bad, but you cannot repair it. The parity block fixes both problems, and it does so with a genuinely clever idea. Send a whole block of bytes. Each byte still carries its own parity bit covering its row. Then send 1 extra byte at the end, the parity byte, whose bits enforce parity down each column. Every single bit in the block is now covered twice, once by its row and once by its column. Let me show you why that matters. Here is a block of 3 bytes with its parity bit column and its parity byte, all using even parity. And at this moment, every row and every column checks out. Now let us corrupt 1 bit in transit. Byte 2, column B4, flips from a 1 to a 0. And notice that nothing about the block looks wrong. The receiver has no idea yet, so it does what it always does. It checks every row. Byte 1 has 4 ones plus a parity bit of 0, an even total, so it passes. Byte 3 passes as well. Byte 2 has 4 ones plus a parity bit of 1, 5, an odd total, so byte 2 fails. That already narrows it to 1 byte. Now it checks every column. Column B4 holds a 1, a 0, and a 0, with a parity bit of 0 underneath. A single 1, which is odd, so column B4 fails. Every other column checks out. Look at what we have. 1 failing row, 1 failing column, and they cross at exactly 1 cell. That cell must be the corrupted bit. There is nowhere else the fault could be and produce these 2 results. And because a bit can only be a 0 or a 1, the receiver does not need to ask for a resend. It simply flips it back. The data is repaired at the receiving end with no retransmission at all. That is worth pausing on because the parity block is the only method in this lesson that corrects as well as detects, and it is a favorite exam point, but state the limit alongside it. It corrects a single flipped bit in the block. If 2 bits are corrupted, 2 rows fail and 2 columns fail, which gives you 4 possible intersections, and no way to tell which 2 of them are the real errors. The error is still detected. You know the block is bad, but it can no longer be located, so it can no longer be corrected. Detecting and correcting are different claims, and the mark scheme distinguishes between them. The third method is the checksum, and it works on a whole block or packet rather than a single byte. The sender runs a calculation across all the data, producing one value, the checksum, and transmits it with the block. The receiver runs the identical calculation on the data that arrived and compares the two values. If they differ, the data changed. The page shows a common algorithm: add the byte values, then take the remainder after dividing by 256. 3 bytes of 200, 145 add up to 345. 345 divided by 256 is 1, remainder 89. So the checksum is 89. And it is worth understanding why that division is there, rather than treating it as a ritual. A checksum has to fit in the space reserved for it, which is 1 byte. 345 does not fit in 8 bits. The modulo makes the value wrap round so that it always does. Change any byte in that packet, and the sum changes, the remainder changes, and the mismatch gives the error away. The fourth method takes a completely different approach. An echo check calculates nothing at all. The receiver simply sends the data straight back to the sender, and the sender compares what came back against what it originally transmitted. If the two are identical, the transmission is assumed to have worked. If they differ, an error occurred and the data is sent again. That sounds robust, but there is an obvious objection, and it is exactly what examiners ask for. If the returned data does not match, the sender knows something went wrong but cannot tell where. The data may have been corrupted on the way out, or it may have arrived perfectly and been corrupted on the way back. Both produce the same symptom, and the sender cannot distinguish between them. Add to that the cost. Every piece of data is transmitted twice, so it is slow and it wastes bandwidth, and you have the two drawbacks that carry the marks. The fifth is the automatic repeat query, and it is different in kind from the other four. ARQ is not a way of spotting corruption. It is the system that decides what to do once corruption is spotted. It combines an error check with acknowledgements and a timer. Watch it run. The sender transmits packet 1 and starts a timer. The receiver checks it, finds no error, and returns a positive acknowledgement, an ACK. The sender moves on. Packet 2 goes out. This time the receiver's error check fails, so it returns a negative acknowledgement, a NAK, which tells the sender explicitly that the packet arrived damaged. The sender retransmits packet 2, and this time it is acknowledged. Now the case that students forget. Packet 3 is sent, and it never arrives at all. It is lost somewhere in the network. Think about what the receiver does now. Nothing. It cannot send a NAK, because it does not know a packet was ever coming. So no reply of any kind comes back, and this is what the timer is for. The sender's timeout expires with neither an ACK nor a NAK, and the sender treats that silence as failure and retransmits automatically. This time it arrives and is acknowledged, so when you describe ARQ, give all three parts: an ACK for success, a NAK for a detected error, and a timeout for a packet that vanished. There is also a resend limit, so that a permanently broken link eventually stops rather than retrying forever. The last method checks something different. Everything so far has checked data that was transmitted. A check digit checks data that was entered, typed by a person or read by a scanner. It is an extra digit on the end of a code, calculated from the digits in front of it. And it is designed around the mistakes people actually make, mistyping a single digit and transposing two adjacent digits, typing 57 as 75. Take the ISBN 10 example on the page. The number is 030640615, and we want the check digit. Multiply each digit by a weight, counting down from 10. 0 times 10, 3 times 9, 0 times 8, 6 times 7, and so on. Those products add up to 130. Divide by 11. 130 is 11 11s, remainder 9. Subtract that remainder from 11, and 11 minus 9 is 2. The check digit is 2, and the complete number is 03064061552. Now, why the descending weights? That is precisely what catches a transposition. If you swap two adjacent digits, each one is multiplied by a different weight than before, so the total changes and the check fails. A plain sum would not notice because addition does not care about order. So, 5 methods and 1 table to keep them straight. 3 things to take into the exam. First, know which one corrects. The parity block corrects a single bit error by intersection. Nothing else here corrects anything. The parity bit, the checksum, the echo check, and the check digit only detect. Second, keep checksum and echo check apart because they are easy to blur together. A checksum is calculated from the data, and only that calculated value is sent back. An echo check sends the whole of the data back and compares it. That difference is also why an echo check cannot tell you which direction the error happened in. Third, when a question asks about RQ, do not stop at ACK and NAK. The timeout is where the marks are because it is the only part that handles a packet which disappeared entirely. And one distinction that catches people out: the check digit is for data entry. Barcodes, ISBNs, account numbers typed in by a human. If a question is about data crossing a network, the check digit is not the answer.